One day, a man saw a white house with a really weird roof. Bam! Just missed the tree. Ouch! His fall. Google graph. Position versus time. Velocity versus time. Acceleration versus time. The Moving Man. The Moving Man fetch animation coming this fall. Available for download on your Java-enabled browser. You control the action.
Okay. Yes, so we will get back to the movie trailer and the Moving Man at the end of today's reading. Basically, so it starts on page 65 of your PDF, section, just one section today, 2.4 on acceleration. And it shows a plane here, which is slowing down. Its acceleration is opposite in direction to its velocity. So there's a definition of average acceleration. You can see here it's the change in velocity divided by the change in time, or VF minus V0 divided by TF minus T0. So this looks very similar to the definition of velocity, which was the change in position per time. And that was meters per second. So this is actually meters per second on the top, per second on the bottom, so you get meters per second squared. So basically, I actually think acceleration is one of the most difficult concepts in this course, and it's also one of the most foundational and important concepts in physics. You can't understand Newton's second law without first understanding acceleration. Newton's second law being that you can find acceleration as being the net force on an object divided by its mass. So you need to know what acceleration is, and if you think it's similar to velocity, you couldn't be more wrong. So for example, what's velocity? It's the rate of change of position. So, and acceleration is the rate of change of velocity. So I would say that acceleration is as different from velocity as velocity is different than position. Okay, you wouldn't confuse where you are with how fast you're going. Well, you shouldn't confuse how fast you're accelerating, or what's your magnitude of your acceleration with your speed. Okay, those are not the same thing. So again, the videos, watching these pre-class videos is not a substitute for doing the reading, and this is very, very important today. I really encourage you to read this section. Misconception alert: deceleration versus negative acceleration. That's important. This all depends on which way you define plus. Okay, something can be decelerating and have positive acceleration, and these are some different examples of acceleration in various different directions and velocity in different directions. But basic idea is that if the velocity vector and the acceleration vector are in the same direction, it means your object is speeding up. If the velocity vector and the acceleration vector are in opposite directions, it means it's slowing down. Just as there was instantaneous velocity as opposed to average velocity, there's also instantaneous acceleration. It just means it's that average acceleration, but over a very small delta t. Okay, so it turns out to be the acceleration at a specific instant of time. And you can graph instantaneous acceleration versus time. There's some important unit conversions. Delta V here is 30 kilometers per hour over 20 seconds. You're going to have to convert kilometers to meters and hours to seconds to get meters and seconds. You're trying to get all the units of distance in meters and all the units of time in seconds to calculate things, and they're called SI units, the System International. And so now for something where the velocity is changing, you've got position versus time. The slope of the position versus time graph becomes your instantaneous velocity versus time. And similarly, the slope of the velocity versus time graph becomes your instantaneous acceleration versus time. So positive slope here, then velocity remains constant, that's zero acceleration. And then when velocity is decreasing, you get a negative acceleration. So I'm going to let you read through all of that. Pretty important. And ends, of course, with the PHY Explorations Moving Man simulation. You click on this, taking you off to this University of Colorado Boulder animation. I really encourage you to try this one out. I would just run the Chirp compatible version. So this is the PHET moving man simulation. Basically, if you give this guy a velocity of +4, for example, then he moves along. And you can see graphs of his position versus time. Here's 6 seconds. So during the first 2 seconds, his position goes up. You can see it's 1.5 meters in 1.2 seconds. 5 divided by 1.2 is 4 meters per second. And here his acceleration is 0. So let's restart this guy at a position of 0. We'll give him an initial velocity of 4. Let's put it to 0 actually, and put his acceleration to +1. Start him off, and he speeds up, speeds up, speeds up, speeds up. Oop, and he hits the wall. So what you see here is now his velocity goes up by 1 meter per second every second. So after 1 second, he's going 1 meter per second. After 4 seconds, he's going 4 meters per second. And his position goes up as a curved parabolic line. If you, let's start him again at 0 position. Let's give him a positive velocity of 4 meters per second and a negative acceleration of 1 meter per second. So he's slowing down. At first, he slows down, reaches a maximum position, then he's speeding up, but going to the left. So let's stop him at 8 seconds and take a look at the graphs. You can see the velocity starts at +4. And let's zoom in on the acceleration. The acceleration is a constant value of -1. So for every second, he loses 1 meter per second of velocity. It goes through 0. This is the turning point when he turns around at the house. And that happens when he's the farthest to the right that he can possibly get. That's about 8 meters. Then it turns around. So once again, this is a parabolic position versus time graph, and his velocity is a straight line with a negative slope. You can sort of see here. It starts off with a positive velocity, goes through 0, then it's a negative velocity as he's moving to the left. So he's slowing down, then he stops, and then he's speeding up. So I really encourage you to play around with that yourself, and definitely do the reading this week, and I'll see you next time when we continue with this chapter 2.